So I wanted to tackle this problem with a cantilevered beam and see if we could come up with the shear and moment diagram for this. The first thing, of course, that we'd need to do is come up with the reactions. And we'll find that we might be able to skip that if we really wanted to, but we're still kind of new at doing this, so we'll be careful here. So I'm going to have a vertical reaction here. I'm going to have this support moment here. I could have a reaction there, but I think you're going to recognize very quickly that that is 0, so we'll write it like that. We've got then this load like this, which is 10 feet of 100 pounds per foot, and then a concentrated load out here of 500 pounds. You might wonder, well, where would I end up with something like this? Well, let's say that maybe you've got a building here and a street where people are walking, and you've got some sort of a cantilevered overhang here, and they put a sign out here, and then you've got some dead load and snow load out there. That's how you could end up with something like that. So it's a fairly common arrangement. Well, let's see if we can solve for these reactions. We'll sum the forces in the vertical, setting that equal to 0. So I'd have R minus 500, and then the area under the load is what, 1,000? So I could say that R is equal to 1,500 pounds. That would be the reaction there. And then if I sum the moment, maybe I'll sum the moment about the right-hand side, setting that equal to 0. I'll go ahead and take clockwise as positive, and I would have then M. I'm summing it about there, so I don't have to worry about R. This M is clockwise. Then I'm going to subtract off 500 times 10, and also have to subtract off, there'd be an equivalent load there. That would be what, 1,000?
What are you summing the moments about?
The right-hand side. So I'd have a 1,000 times 5, right? Because that would be acting at the center of that. So I could say that M is equal to 500 times 10 plus 1,000 times 5, which is going to get me what, 5,000 plus another 5,000 equals 10,000 pound-feet. Did I do that right? I think so. Questions with that so far? Okay, so I got the reactions. Let me see if I can draw the shear and moment diagram then. I'll start out like we oftentimes do with a picture of or a diagram of the beam. We know this reaction is 1,500 pounds. We've got this supporting moment here of 10,000 pound-feet. Let's see, then the distributed load. And then this load that we would add out here of 500. And this is, of course, 100 pounds per foot and 10 feet. So we're going to come up with something that looks like this. And here's our shear. That's going to be in pounds. I think this is one of the first times we've done this with numbers and units. So that would be our unit, a force unit. Pounds are probably newtons. So what do our rules say? We're going to start at the left-hand side. We're going to start at 0. So we start right there. And immediately we have this concentrated load. So we jump down. We jump down 500. And then the change in the shear is equal to negative the area under the load. Well, what's the area under the load? Area is going to be equal to 10 times 100, isn't it? So that is 1,000. So if I take minus 1,000, that puts me at what? Minus 1,500. 500 minus 1,000. So I have minus 500, I have minus 1,500. And I know I get there if this is a constant value, constant positive value, I'm going to get there with a constant negative slope, aren't I? And before I claim that I'm done, I guess I need to deal with this reaction here. If I'm down here at minus 1500, I would jump back up to 0, right? And that's actually where I'm saying if with this problem, we could have not found these reactions here because we would know that it would jump back to 0, but it's kind of nice to know that this is 1500, and we do confirm that it gets back to 0. So that's what our shear looks like. Questions on that? Then the moment is going to be negative, so I'll draw the moment line fairly high. So here is our moment in pound-feet. We're going to start at the left-hand side. We're going to start at 0. Do you have any concentrated moments? Well, we don't get to a concentrated moment until we get to the right-hand side, so we don't have to worry about that yet. And we know that the change in the moment is equal to the area under the shear, right? So what's the area under this thing? Well, we're going to have 1500 plus 500 divided by 2 times this distance across here, which is 10, right? So what's that? 10,000? And it's below the line, so we would take this as negative. So we're going to be down here at minus 10,000. And how do we get to that point? Well, we know that the slope of the moment is equal to the value of the shear. So the value of the shear is a small number there, small negative. So we're going to have a small negative slope going to a larger negative slope. So we'll have a second order curve. A small slope here. The tangent line has a small slope. Tangent line has a large negative slope there. So then I get down here. How do I get back to 0? Well, I have this concentrated moment. It's clockwise. What does a clockwise moment do? It jumps up. So if we're at minus 10,000, we jump back up to 10,000. It gets us to 0. So we can start to have some confidence in this answer. So that's our shear and moment diagram. So if the architect comes in here and wants to design this a little bit differently, wants to design this with maybe a beam that allows more light into the buildings or something like that and starts to taper off that end, what do we think? We might be able to do it, right? Yeah, because the largest shear and the largest moment is here at the support. I've kind of switched these on you. I've drawn one to the right and one to the left. But if we were to draw this beam, we could taper this beam down probably rather significantly over here, right? If this is the beam itself. Okay. So, just a thought. Questions on that? A couple other things that come up. Yeah, maybe I'll finish up with this next problem before we get into that. This is a problem I told you. This is actually up on the website. I think we did this in statics also. I think it's a good problem. If you can tackle something like this, you're in pretty good shape on this. It has a lot of different pieces, distributed loads, triangular loads, concentrated moments, cantilevered sections. So you can figure out how you want to do this. If you want to follow along, that's fine. If not, the notes are up on the website, or we'll of course be posting this lecture afterwards. So in going through this, I've got this in the already in a free body diagram. So what I'm going to do is I'm going to have to solve for the reaction at A and the reaction at B. Let's see if I can do that. I think what I will do is I'll just sum the moment about B. So summing the moment about point B there at the right-hand side, setting that equal to 0. Maybe I'll take counterclockwise as positive. What are we going to have to deal with? Well, let's see. What's the area under this piece? I have 6 times, and this is 100, so this would be 300. And what distance is that acting through? Let's see, I have 2, and 6 gives me 8. 2 more gives me 10. and then that's going to act at the 1/3 point. What's a third of 6? 2? Okay, so that would 10 and 2 gives me 12. So again, where that comes from is that's going to be 2 plus 6 plus 2 plus 6/3. And I need to add that to, I can do this whole area here. What's that going to be? 8, because 2 and 6, that's 8 times 100. So I'll have 800. And what distance does that act through? It's going to be at the center of that, which will be 4 from there. So it'll be right there. So 4 is 6. So I have 4 from that point and 2 there, so it should be 6. Anything else? I'm going to have to subtract off this 2,000, because that's a free vector. It'd have to be included in no matter where we're summing the moment about. So I've taken care of the area here. I've taken care of that triangular area. I guess I would also need to subtract off the force A times the distance that acts through, which is 8. So A turns out with that equation to be equal to 300 times 12 plus 800 times 6. Let's see, minus 2,000 divided by 8. Come up with 800. That's what I got. 800 pounds. So then we could probably just sum the forces in the vertical direction. Setting that equal to 0, I would have A plus B, that's acting up, and then I have to subtract off what? The area of this is going to be 300, and the area of that we said was 800. So we could put this in for A, solve for B. B turns out to be equal to 300 plus 800 minus 800. So B is equal to 300 pounds. Anyone else get that? So this is 300 and this is 800. Which is pretty standard. When you have a cantilever section like that, usually the reaction at the cantilever section is fairly large. And it would be even larger if we didn't have that concentrated moment in that direction. So that's good. Questions on the reactions? So now that we got the reactions, we can start the shear and moment diagram. We'll use the shortcut method. I'm going to start the shear here at the left-hand side at 0. And we know that the change in the shear is equal to minus the area under this. So what was the area that we had for this? That was 300, wasn't it? So it's going to drop down to, that's positive, so I put a negative sign in front of it, so I have minus 300. And how do I get there? This is a constant, or this is a positive number that's increasing, right? So when I put a negative sign on that, I would get a negative slope that's increasing. So something like that. Okay. And then I have this piece in here. What's the area there? 200. So I subtract that off. That takes me to minus 500, because minus 300 less 200 is minus 500. And how do I get there? If this was second order, this is a constant now, so this is going to be what? Linear, right? So that'll be linear. That'll be first order. And then I don't want to forget about, get so involved with these areas, I forget about these forces, which are the reactions. So I'm at minus 500, and I now jump up 800, so that's going to take me where? Positive 300, right? If you're at minus 500 and you add 800, you jump up 800, you'll be there. Okay. And then we start subtracting area again. The area under this is 6 times 100, or 600. So that'll take me back to minus 300, right? And I get there in a linear fashion, like that. Now this point where this crosses is probably going to be something that'll be interesting on our moment diagram. And if we look at this, we essentially have a situation here where we've got a triangle. Like this, where this side is 300, this side is 300, and if I say that this is some unknown x, I know that this, what's left over here, has to be 6 minus x, because this total distance across here is 6, right? Because this angle is the same as that, you know that from geometry, right? You can say that that x is to 300 as 6 minus x is to that 300, and you get that x is equal to 3, right? So you probably wouldn't have to necessarily do it for that one, but sometimes it's not obvious. So that's how we know that this is 3. Questions so far? So does this concentrated moment show up directly on the shear diagram? No, we don't do any jumping around on the shear diagram to do that. It does show up. It's changed our reactions, and our reactions show up on the shear diagram, but it doesn't show up directly. So I'm sitting at this point. Now what do I do? I just continue on, don't I? A lot of people like to jump back. They don't see any load there, so they want to jump down. No, you just continue on. And then if we're at minus 300 and we jump up 300, that's going to put us back at 0, right? So that's minus 300. So that's our shear diagram. Questions with that? Well, let's try the moment diagram. If you have questions, I can come back to it. So the moment diagram, again, we start at 0 at the left-hand side. Remember, we've got a concentrated moment. Those don't show up that much, so don't forget about them. We'll start at 0. And, oh, I need to find the area under this one, don't I? What's the area there? Area under a second-order curve becomes a problem, doesn't it? So what I might do is I might just take a quick section at x equals 6 feet. So that's going to look something like this. So I have 6 feet here, and there is the shear according to the deformation sign convention. Here's the moment. And if I wanted to, I mean, I could sum the forces in the vertical direction, setting those equal to 0. I would have minus v minus, what is this? This is 100 here, so minus 300. So v turns out to be equal to minus 300. We already kind of knew that, didn't we? It's a nice confirmation there. So I technically really don't need this. What I really need to do is sum the moment about the cut point. Setting that equal to 0, what do I have? I could say that I have m plus, I'm still going to have 300. And what distance is that going to be acting through? This 300 will be acting down like that. It's going to be acting at 6 over 3, isn't it? Okay, so I come up with m is equal to minus 600 pound-feet. So I can draw that right here. There's minus 600. There we are. Now how do I get there? If this is second order, what order is this? Third order. Okay, so there's third order.
Why is it 6 over 3 levels? Oh, is that?
Those are the easy questions. Okay. So we got that. Now we have to figure out the area under this trapezoid here, right? So you can do it a couple different ways. You could do a rectangle and a triangle, or we could just average this. The average of 300 and 500 is 400, so you multiply that by 2. So you got 800, so if I'm minus 600 and I subtract another 800, where does that put me? Minus 1400? And how do I get there? If this is linear, I'm going to go to a second order curve, aren't I? And normally you don't put the 3 and the 2 there, but I'm just doing that as we're doing instruction here. So you go from a third order curve to a second order curve. Then what happens? You got some area under here, right? What's that area going to be? Well, that's why it was important that we found out that it was crossed at the center, that this was 3, because now we have 3 times 300 divided by 2. So it's what, 450? So this is positive 450. So what do? I add that, right? So that's going to take me to a point there that is, what? Minus 1400 plus 450 gets me to minus 950. That came from minus 1400 plus 450. And I didn't write 450, did I? So that should be 450. Okay, how do I get there? I start out with a large positive slope and go to a small positive slope, something like that. Now, what's the area under this one? Minus 450, isn't it? So easy come, easy go. I'm right back down to here at that minus 1400, like that. And here's where you can get into trouble. You get used to just going along, and you sometimes forget this, but we don't want to. We have a clockwise moment of 2,000, so that means it's going to be an upward jump of 2,000. So I'm sitting at minus 1,400. I have an upward jump of 2,000, so where does that take me to? Positive 600, right? Positive 600. Which is good, because what's the area under here? 300 times 2 minus 600, right? Because it's below the line. So then I subtract off that 600, and this is a constant, so this will have a constant negative slope. So there's what the moment diagram looks like for that. So if someone wanted to come along and drill a hole in this thing, where would we definitely not want them working? Around A seems like a bad spot, right? Okay, and probably in this area is not very good either. Someone wanted to come along and drill a hole here, probably okay, right? So we'll talk a lot more about this later in the term, but these shear moment diagrams become very important in predicting those values. Questions with that? So like I say, that's a good example. If you can sit down and do an example like that on your own, I think you're in pretty good shape. You've got the homework problems that are through section A. You want to keep practicing on those. Let me talk about one thing that comes up in a homework problem. I think sometimes there's a problem that looks like this or something like it, where they put this little leg up here. And they put a force on this, and maybe it's got some distance d there. And you're asked to come up with a shear and moment diagram. Well, what we want to do is, in most cases, we want to turn this into something that we've seen before. So let's see if we can do that. we could reduce this force at this distance to an equivalent force, right? So that force is still there, which is going to be an axial force. So that's not going to show up on the shear or the moment diagram, but it would show up in the axial force. But by moving this down, what do I also have to put on here? I have to put this moment on here that's going to be equal to what? Force times the distance d, right? Now, could you tackle something like that? Yeah, you can tackle something like that. So I think you've got a homework problem like that. Don't let it throw you. Questions with that? So with that, we're not going to go back and spend any more time with shear and moment diagrams. We will bump into them again when we later on in the term when we start to talk about beams and bending. I wanted to give you plenty of time to practice them so you're very comfortable with them because like I said before, we tackle some equations here. The shear stress later on in the term, tau, is going to be VQ divided by IB. If you can't get the shear stress right, it's going to be hopeless coming up with the, if you can't get the shear value right, coming up with the shear stress is going to be very difficult, very hopeless. So we got to get the right shear value. And then we'll talk about normal stress due to bending. That's the tension or the compression in the beam. That's going to be equal to minus my divided by I. So there's that m value. That's your moment. So if you can't get those two right, you can't get the stresses right. If you can't get the stresses right, you're going to have problems. So we'll have several quizzes between now and when we tackle this in the beam design section. Make sure that you're getting this figured out, passing those quizzes, and able to do your shear and moment diagrams. Questions with that part of it? Well, let's go back and start at the beginning of the textbook, maybe even the beginning of the class, when they talk about strengths of materials or mechanics of materials. Sometimes people confuse this with material science. That's usually more on a microscopic level. But this material, what we're talking about, would go by a couple of names now: strengths of materials or mechanics of materials. And the first thing we will often talk about in there is we're going to talk about stress and strain. Okay, and remember that we're no longer thinking about things as rigid bodies. They're not staying at constant dimensions. So having them strain, having them change in dimension is something that we can now tolerate. The first thing we'll look at is uniaxial stress. Uniaxial stress is by definition stress in only one direction. Eventually we'll get to triaxial stress. When you see that, we'll make the comment that we could study that first, and this is just a special case of that, but that'd be a little bit like saying crawling is just a special case of running, so you should learn to run first. That probably doesn't make a lot of sense. So we'll start out with this. It's probably a little bit easier just looking at stress in one direction, but we will start to look at others eventually. So let's say that we have a bar with some load on it. So we'll put some axial load into this thing. And we could put a compressive load on it, but I'm going to take a tension load. And if I were to slice through this thing right here, what we would have would look something like this. And we'd need this to be in equilibrium, so we could put this internal force, if you will, across the surface there, and we still have the load on this P, and we would say that this would be the stress. This is what we call our average normal stress. Our average normal stress, which we can say is sigma, which would be the force P divided by A. Okay, sigma is P over A. So average, where does that word come from? Well, if we have a notch on this thing or a hole in this thing, or we're looking close to the end of this, we're going to have some discontinuities and some disturbances. If you have a notch or a hole, you can have some stress concentrations. So we're saying we're not talking about those. We're just talking about average. Okay, if we average across the surface, and I'll talk about stress concentration later. Normal, that just means perpendicular. So if we look at the axes that the load is put on, that's this axial direction, and we're looking at a surface that is perpendicular, that is normal to that axial direction. So that's where we get the phrase average normal stress, and we can say that that's simply the force divided by the area. Okay. So the units on this thing would look something like this, pounds per square inch, which we say is PSI, or we might talk about 1,000 of those, which would give us KSI. KSI is just 1,000 PSI. A Pascal, of course, is a Newton per square meter, which is an incredibly small unit. So usually we talk about megapascals, which is, of course, 10 to 6 pascals, or maybe even gigapascals before we're done, which is 10 to the 9 pascals. Because a Newton is smaller than a pound. Meter is quite a bit larger. Square meter is quite a bit larger than a square inch. So if we have thousands of PSI, we would have lots and lots of pascals. The sign convention.
Is that a capital N Pascal?
Yeah, capital N, mega. Because little m would be milli.
Right.
Yeah. So if we look at the sign convention, fairly easy. Tension is positive. So in the case that I drew there, I drew it in tension, so it would have a positive value. And we're going to see this equation come up again and again for different types of stresses. It may have different symbols in there, but usually the difficult part is, one, figuring out what the force is. That's why you did the quiz last week, so you could figure out those internal forces in axial cases. And then what is the area? What area is it acting over? So that'll always be a big piece. So that's stress. That deals with the internal forces, force acting over an area. So now we want to go on and we want to look at strain. That's the flip side of this, the other part of it. So we'll talk about normal strain. So looking at normal strain, I guess this was what, page 4, page 5. So with normal strain, again, if we look at this, we take this bar here, and maybe it's unloaded at this point, and then we decide to load it, so we'll say no load. And then we come over here and we decide to load this thing. What's it going to do when we load it? Probably going to get longer, right? Okay, so we'll put this load on at P. So say with load. Okay, and if we look at this, this has got longer. Okay? If you take the table legs over there, you put a big weight on the table, it's going to get shorter. It's going to compress the table legs. Or if you reach down and grab the table legs and you pull on them, they're going to get longer. You're going to stretch them out. We're going to say that this is delta. And we could say that normal strain is defined as epsilon. We're going to use a lot of Greek letters. There's epsilon. Epsilon is equal to delta, that's lowercase delta, divided by L, okay, which is the change in the length divided by the original length. Okay, and this is really engineering strain. If you want to look at a kind of a side here is true strain. We use the current length, okay? So when we talk about engineering strain, which is what we're going to talk about for the rest of this term, we use the original length. for materials like wood, concrete, and steel, they don't stretch that much. So whether we're using the current length that it's stretched or whether we're using the original length before it started to stretch, it doesn't make that much difference. When you start looking at plastics and rubbery type materials and things like that, it can make a huge difference. So a lot of times you'll talk about true strain. So that's just kind of a aside. So the change in length over the original length. What are the units on this thing? Maybe I better be real clear. This is what we are going to use. Whereas this is just FYI. You go into material science, they'll talk about true strain. So if I look at units, what units do we have on this thing? Well, probably inches. Change in length, that'd be inches. Inches over inches, which would be no units. Or maybe millimeters over millimeters. Or meters over meters. So it's really unitless, isn't it? Okay, it's unitless. The big thing you have to be careful of is mixing units, because oftentimes delta, we might measure in thousandths of inches, right? It could be a very small number. Whereas the length, we might be tempted to measure in whole inches or feet or something like that. So make sure that you have consistent units so that you can get those things to cancel out. So if we look at a coordinate system here, let me just go ahead and take x like this and y like this, and well, no, I don't want to. I'll take this as y. Let me say that this is z. So yeah, that'd be a right-hand system. So I'll take this as z. Okay. So this is z. So we could say that epsilon in the y direction is equal to delta over L. The question might come up, what is epsilon in the x and epsilon in the z? Well, for now, we're just going to say that they're not equal to 0. Okay. You recognize that, what's that? Yeah, we're okay with that? Okay. So you recognize as you pull on something, particularly if you do something like silly putty, it gets smaller in cross-section, so it has to have some strain there, right? And we're going to have a number of Poisson's ratio that's going to help us relate those two. But for now, we'll just say it's not equal to 0. Okay? And leave it like that. So let's try a quick problem here. Any questions? So 6. So the equations that we have at our disposal, it wouldn't hurt us to keep rewriting these. We now have that stress is equal to force divided by area. We have that strain epsilon is equal to delta over L. There's going to be lots of little equations that we need to get comfortable with. So let's say that someone gives us a sample here. We put 10 kilonewtons here. We have 10 kilonewtons here, so I'm switching up units on you. We'll say this starts out at 1.5 meters in length. The cross-section is given as a 10 millimeter diameter. And we're told the bar stretches. Stretches 0.5 millimeters. So we put that load on and it stretches, and we would like to find then, we'd like to find sigma x and epsilon x. So I'll say that this is my x direction. Okay, so epsilon x, or sigma x, what's sigma x going to be? Well, force over area, right? That's this one. So what are we going to have? The force, 10 kilonewtons, divided by the area. What area am I going to have? $10 millimeter diameter. So what's the radius on that thing? 5 millimeters. Okay. So I would have pi times 5 squared, and that's going to be millimeters squared. So I'd come up with 0.127 kilonewtons per millimeter squared. It's kind of a weird unit. So I need to change this a little bit. I could say then that this would be 127 times 10 to the 6th newtons per square meter. So I'd have to multiply by what, 1,000 squared or a million to get the denominator, and then I'd have to divide or multiply by another 1,000 for the K. So I could say that this was what, 127 megapascals? megapascals. So that was the stress. How about the strain? Well, we know epsilon x is going to be equal to delta over L. And what we're told about this, it stretches 0.5 millimeters. Okay? So I'm going to have 0.5 millimeters in the numerator. And then the length is 1.5 meters, and this is what I was telling you don't want to do. You can have units problems there, so I need to get consistent units. I have that 1 meter is 1,000 millimeters. So now I have consistent units, and you're going to have a 3.3 times 10 to the minus 4. And that'll be unitless. And this follows the normal trends. Typically our stress values are very large values, megapascals, kilo psi, and our strain values are usually very small. Questions with that? Did you get those same answers? Yeah.
Could we do the same stuff with an accelerating rod if the forces were not equal?
Yeah, we're not.
10 kN and then we get 7 kN.
Yeah, we're not going to get into that, but yeah, it would be accelerating, and then you just look at the net. So yes.
I was wondering how realistic are these values, and that if you had a rod that was 1.5 meters and it was experienced 10 kilonewtons of force on each side, is it typical that it might stretch by about 0.5 millimeters?
Oh yeah, yeah. That's the big thing that I was going to mention. We haven't committed to the material, so if this was steel or aluminum or wood, it could vary dramatically. But you could take the table leg there on the table that you have, and you could get it to stretch a 0.5 millimeter and still not tear it in two.
What about like a skyscraper?
Oh, it'll stretch a lot. They move a lot. Yeah, they move a lot. Yes?
So, jumping ahead to a few years, if you were designing something, there's a lot of the values for the strength of material we would be using kind of given to us.
Yeah, you're going to have some tables, or for the civil engineers, that's the difference between good material and bad material would be the certification. If somewhere along the process we lose the certification, you lose about 90% of the materials values, because then we don't really know what it is. So that's going to be a big issue, and you're going to well know that, what the material values are. Well, speaking of that, where we're going to go next is we're going to look at, let's say that we have a sample. So there we've got something like this. And what we're going to do is we're going to start to pull this apart. So we're going to put some force on here, let's say some tension. And because we can measure the tension, we're going to measure the tension, which is going to allow us to get the stress, because the stress is going to be the tension divided by the area, right? Okay, so if I take a specimen that looks something like that, that one's probably kind of hard to see on the camera because it's a piece of plastic. Here's one that's aluminum. Okay, and this one has been torn apart. And these started out at about the same length. So the question came up, how much stretch do you get? You can get quite a bit of stretch out of these things before they fail. Now, most of what we're going to work with, and we'll see when we get to the stress-strain curve, is we're going to work in the linear region, which means they'll snap back. These obviously have gone a long ways past where they'll snap back. Okay? So we're going to measure the tension and we can measure the stress. We're also going to measure delta. So with delta, we could get the strain, because the strain is delta over the original length, right? And then what we're going to do is we're going to plot the strain and the stress. And if we get something that does something like this, comes up and breaks, we'll know we have a relatively brittle material. Whereas if we have something that comes up and goes like this, we'll have a much more ductile material. And probably if we're building bridges, we would like to build them out of ductile material, right? No one would like to build something out of brittle material if you want it to absorb loads and things like that. So we'll talk a lot more about this. We'll talk about these stress-strain curves and how we can actually test something. We can take some material and we can do tests on it to see what we have. So that's where we'll head in the future. Take care till then.
Yeah.